Okay, so we've graphed some polynomials, and now we're going to talk about another type of graph that you should have some knowledge of when you go into calculus, which is graphing rational functions. Rational functions just mean fractions. So functions that are fractions, which often have both vertical and horizontal asymptotes. We'll talk about that in a second here. So probably the most basic rational function is just f of x equals 1 over x. Notice, okay, domain is a big topic we've talked about. If I asked you what the domain is, what's the one number you would not be allowed to plug in for x? You could definitely not plug in 0, right? You'd end up with 1 over 0. Also, I want to notice and point out that something we've talked about earlier, which is the idea of an odd or even function. If you plug in negative x for x, you just get 1 over negative x, which is just the opposite of what we started with. So that tells us that f of x is an odd function. Okay, it means it's going to have symmetry about the origin. So we'll keep these two things in mind as we sketch this. So let's plot some points here. I've got some comments which we'll fill in, but anytime you don't know what a graph looks like, we can just start plugging in points. If I plug in 1, I get the point 1, 1. Just plot that there. I'm going to go for fractions now. If I plug in 1/2, 1 over 1/2 is actually 2. So you would end up with the point 1/2 comma 2. If you plug in 1/3, 1 over 1/3 is actually 3. 1/3, 3. And you start to think about this. If you plug in a small fraction, like let's say 1/10, 1 over 1/10 is actually 10. What if x was 1 over 100? 1 over 1/100 would be 100. So the smaller x gets, the closer it gets to 0, we start to get bigger and bigger fractions. Here, I'll put like, what did I say? 1/10 and 10, that's one of them. So we can start to see that the graph, as it approaches x equals 0 from the right side, the y-axis, it's getting infinitely big. And that's why we put a vertical asymptote here to indicate that our graph is starting to approach the y-axis as we plug in x values that get really, really close to 0. So vertical asymptote at x equals 0, because as the x values get close to 0, my f of x values, my y values, will start to get close to, if you think about it, they're going to get infinitely big. So that's why we have that vertical asymptote there. Now let's try some numbers bigger than 1. If I plug in 2, I get 1/2. So that might be like right here, 2, 1/2. If I skip all the way to like 5, I get 1/5. And hopefully you can see that I have kind of a similar issue going on. If I plug in bigger and bigger x values, right? If I skipped over here and did 10, this would be 1/10, which would be really, really small, but still positive, still positive. Maybe I need to continue this. So we put a horizontal asymptote, which is the x-axis, also known as y equals 0, to indicate that as my x values get really big, my f of x values start to approach 0. They're getting closer to 0. And that's how we can denote it. That means it's going to get infinitely close, but never quite make it to 0. Now, the fact that this is an odd function, remember, means that for all of my negative x values, I just get the opposite of my y values, right? I get the opposite of my y values. And so that instead of 1, 1, I would get -1, -1. Or you can, that idea of being an odd function, if you can imagine reflecting this about the y-axis, so you have something like this, and then reflect it about the x-axis, you get a graph. I haven't done a great job, but that's kind of like reflecting it about like a diagonal line. You would get this part of the graph over there. Okay, so you can probably guess that there's going to be more involved when we're graphing rational functions than with polynomials. But when you go back to polynomials, just like the bounce and through idea that we talked about in terms of the x-intercepts on a polynomial, or really any kind of function that had to do with the exponents, there's a similar quote unquote shortcut that tells us how the graph behaves on either side of my vertical asymptote. So this is a little, not every book mentions this. This is something that I find really helpful when I'm graphing rational functions. So let's take a close look at this page here. And what you want to think about is, what do you notice about how the graph behaves on either side of the vertical asymptote? Here's the graph we just did, y equals 1 over x. So what do I mean by that? On one side of the vertical asymptote, on the right side, as the graph approaches it, it goes up towards infinity. But on the other side, as a graph gets closer, it goes to the negative infinity. So that means they're going in opposite directions, huh? One's going to infinity, the other one's going to negative infinity. That's what I classify as opposite. Whereas on this graph, on the left side, as we get close to the asymptote, which is 0 for all of these functions. Okay, we'll talk about that. This side goes up to infinity. And if I approach x equals 0 from the right side, it also goes to infinity. So this situation, I classify that as opposite. And this one I would classify as same. Both sides of the vertical asymptote, the graph is doing the same thing. Okay, now the vertical asymptote, for now, we'll just say, well, we're going to update this as we go forward. But if you've got a fraction like this where it's undefined, right? Both of these are undefined when x is 0. So it's when the bottom is 0, right? This one has a vertical asymptote, x equals 0, as does this one, because x squared, if I set that equal to 0, I also get 0. Okay. Now here's what I want to show you. Here's some more graphs. Y equals 1 over x cubed actually kind of looks like a more narrow version of y equals 1 over x. It kind of hugs the axes closer as it approaches the asymptotes much faster than y equals 1 over x. Okay. But how would you classify that? That would be another opposite. Y equals 1 over x to the 4th is a more narrow version of y equals 1 over x squared. So that would get classified as same. And just to mix it up a little bit, here's y equals negative 1 over x to the 5th, which would look kind of like this one, but reflected over the y-axis. And again, more approaches the x and y axes much faster than y equals 1 over x cubed. But once again, that would be classified as opposite. And here's y equals negative 1 over x to the 6th, which this time the graph goes down on both sides of the vertical asymptote, but they both do the same thing. So hopefully you're noticing something. How can we tell if the graph goes in opposite directions on either side of the vertical asymptote? They all of these, the vertical asymptote is coming from an odd power. If your vertical asymptote is coming from an odd power of x, then you can be assured that when that vertical asymptote, if on one side the graph goes down, on the other side it goes up, or vice versa. Whereas if your vertical asymptote is coming from an even power, the graph goes in the same direction on either side of the vertical asymptote. So if on one side your graph happens to go down to negative infinity, on the other side it's going to do the same thing. Okay, so this is super useful. You'll see as we graph some more of these, I think, in graphing, helping us construct the graph. So let's start with this one. Okay, so we want to construct the whole graph. So it's nice to have some points that I can just easily add to my graph. And we've seen in various kinds of functions that easy points to find are y-intercepts and x-intercepts. Your y-intercept is just whatever you get for y when you let x be 0. That's easy to do. You can most of the time do it in your head. If x is 0, I'm going to get 6 over negative 2, which is negative 3. And my x-intercept I find by setting my function equal to 0. Okay, you're going to be doing this quite a bit when you're doing x-intercepts, setting a fraction equal to 0. And there's a couple of ways to explain it. When does a fraction equal 0? If you think about fractions that equal 0, I'm going to write up here, 0 over 7 equals 0. 0 over negative 5 equals 0. What about 3 over 0. That doesn't equal 0, right? 3 over 0 is actually undefined. So the only way a fraction could be equal to 0 is if the top is 0. So setting this equal to 0 is the equivalent to just finding out what makes x plus 6 equal to 0. Now, of course, another way to explain it is to just do the algebra. If you were to do the algebra, what you would do is multiply both sides by the denominator, x minus 2, which cancels here, and x minus 2 times 0 is still 0. So, but the quick way to do it is when you're setting a fraction equal to 0 is just focus on the numerator. This gives me x equals negative 6. Still remember, things we've learned this quarter still apply. This is an x-intercept. And when we were talking about polynomials, we talked about the idea of x-intercepts either bouncing off the x-axis or going through the x-axis. So that still applies. This negative 6 came from x plus 6, which is a factor to the first power. It's an odd power. So I know that this x-intercept is going to go through. If you're not sure what I mean by that, watch some of the previous videos on polynomials. Okay, so what about when the bottom is 0, as we saw on the page before, that's actually where you have a vertical asymptote. For now, we're going to update that right for now, but my function is undefined here. I'll write f of x is undefined when x minus 2 is equal to 0, which gives me x equals 2. But now we can classify this vertical asymptote as either opposite or same. And remember, that has to do with the power as well. This factor on the bottom is x minus 2 to the first power. That is an odd power, so this vertical asymptote would be classified as opposite. Okay, let's talk about what we mean by that. So here I've drawn the graph. Well, I've put some axes here. So I know I have a vertical asymptote at x equals 2. I know I have, let's see, a y-intercept of 0, negative 3. And I have an x-intercept of negative 6, 0. Yeah, negative 6, 0, that's over here. Okay, so we know this is a through intercept, so it's either going through like this or like this. We'll fix that later. And again, by opposite, what we mean is if the graph happens to go on the left side, go up, the other side's going to go down, or vice versa, right? If this side goes up, then this side would go down. Now, one more feature of our graph, HA, that's what I mean, that's my shorthand for horizontal asymptote. And what we saw on the first page, when we talked about y equals 1 over x, when we find a horizontal asymptote, what we're thinking about is what is your y value approaching as x gets really, really big? And in fact, we can write this. I'm going to introduce a little bit of calculus notation for you here. When you get to calculus, asking this question, what does y approach as x gets really, really big? You can express that as a limit. I better stick with glue. So we write this in calculus. LIM is just short for limit. As x approaches infinity, right? That's what we mean by big, of the function 1 over x. You can kind of see it. If I imagine x being an infinitely big number, I am going to get 0. That's why that is our answer here. So I personally think if you're taking pre-calculus with plans of taking calculus, we might as well start talking about calculus. So to find our horizontal asymptote, I am going to go ahead and use this limit notation. We want to find out what does y approach as x goes to infinity, and we'll talk about negative infinity as well. Let's start with positive infinity. Different books, if you're in a different class besides mine, they might use something slightly different, but you'll see we're talking about the same thing. If x is getting really, really big, if it's infinity, infinity plus 6 is an infinitely large number. Infinity minus 2 is an infinitely large number. So we have a really big number over a really big number. Now you got to be careful because usually when you see the same thing over the same thing, your instinct is to say it's equal to 1. But remember that infinity is not really a set number. So we can't automatically say that this is equal to 1. So one way to sort this out is to rewrite this fraction. And what I can do is I'm going to divide every term by x. We'll talk about that in a second of why I'm doing that, or yeah, why x. So if I take a fraction, as long as I divide everybody by the same thing, then all is good and well. I haven't changed anything. But what it allows me to do is get a different look at this function. X over x is 1 plus 6 over x. This is 1 minus 2 over x. And it's a lot easier to see now that if x was a really, really big number, what would happen to 6 over a really, really big number, right? If I had 6 over the biggest number you could think of, right? Isn't that going to be really small, right? It's going to be a tiny number. It's going to be like 0.00000 something. So small, if we take it to the extreme, that will get infinitely small. We could say that approaches 0. That's kind of the notation. A lot of times you draw a little arrow through it and say it's going to approach 0 as x goes to infinity. Same thing here, right? 2 over a really big number is going to get really, really small. So what does that leave me with? If both of these are 0, I do end up with 1 over 1, which is 1. So my horizontal asymptote is y equals 1. That would be like right here. And that's the idea if we draw this dashed line to show that my function is going to approach y equals 1. Oh, okay, one other thing to talk about here. Certainly as x gets really big, notice that if x went to plus or minus infinity, isn't it true 6 over, if I made this 6 over negative 10 gazillion, isn't that also getting really small, right? So whether x went to plus or minus infinity, in other words, as the graph, as we proceed in this direction or this direction, my y values will approach 1. Okay, so that's why we draw the asymptote all the way through. So now let's get we've got everything we can do right now. Let's try to figure out what this graph looks like. If we take this part right here, we know this is a through intercept, and we know it has to approach this asymptote in this direction. So it seems, doesn't it seem more likely that the graph would cross through here and approach y equals 1 in this direction? And it also has to hit this point. So that also makes sense that it would, well, let's pretend this is 0, -3, just to. Now, as you get close to a vertical asymptote, right, we've already got it coming here. All indications are it's just going to keep going down and approach the vertical asymptote, go to negative infinity, right? And you can confirm that. If you plug in, like, for example, f of 1, if I plug in 1 into my function, 1 plus 6 is 7, 1 minus 2 is -1. So I know another point that is on this graph is 1, -7, which kind of confirms it's continuing downward, right? You can always plug in points if you're not sure what your graph looks like to generate more points. Now, remember we classified this vertical asymptote as opposite. So now that we know that on the left side it goes down, that means on the right side, the graph must be going up as we get close to 2. There are no more x-intercepts, and we know it has to approach y equals 1. So the most likely situation is the graph is just going to curve and approach this horizontal asymptote y equals 1. And so there's our graph. Let's practice some more. I want to graph now f of x equals 2x squared times x squared minus 9. One thing, okay, we've been talking about even and odd functions. You might, when you see both of these being x squared, you might suspect that this is an even function, and we can certainly confirm that. F of negative x is going to be 2 times negative x squared over negative x squared minus 9, which is exactly the same. That's 2x squared over x squared minus 9, which is my original function. So we can conclude this is an even function. So that might be useful when we're drawing the graph. We know it's going to have symmetry about the y-axis. All right. Let's generate some points. I usually, despite what I did on the last problem, I usually start with X-intercepts. And the reason why, so I'd be setting the function equal to 0. We know that when you set a fraction equal to 0, it's really just about the numerator. And of course, the only number that makes that equal to 0 is 0. And it's coming from an even power. So remember, for X-intercepts, that we would classify this as it's bouncing off the X-axis. Now, the reason I start with the X-intercept is because if one of my X-intercepts is 0, wouldn't that be my one and only Y-intercept, right? So I don't need to bother with a Y-intercept if I've already found an X-intercept and it happens to be 0. So what I would do next is go for my vertical asymptote. And that's where f of x is undefined. And that's going to come from the bottom, x squared minus 9. Now, just like with the bouncing through thing, if you want to identify whether the vertical asymptote is opposite or same, you do want to have it factored completely. This is x plus 3, x minus 3. So I get vertical asymptotes of -3 and +3. And since both of them come from factors to the first power, which is an odd number, both of these are going to be opposite. And then lastly, we'll find our horizontal asymptote by trying to find out what my limit is. What is my function approaching? Let's just start with positive infinity. And like I did last time, we can think about the negative infinity after we decide what happens. Okay, so here, if we imagine x being a really infinitely big number, infinity squared is infinity times 2 is definitely infinity. Infinity squared is definitely infinity. Oh, subtract 9 from that. That's not going to matter, right? That's still going to be an infinitely large number. Last time when we saw infinity over infinity, it actually equaled 1, which is maybe what you would think it would be. But watch out on this one. Now, how we're going to sort this one out, and here's where I need to now clarify my strategy. I'm going to rewrite this fraction, this time not dividing everybody by x like I did on the last one. This time I'm going to divide everybody by x squared. So what's my rule? When I get infinity over infinity, what I'm going to do is divide each term by the full rule is this: the biggest power in the bottom. Now, the biggest power on the bottom is x squared. That's the same as the biggest power on the top, but there will be a situation when that does matter, when you want to stick with the bottom instead of the top. That's coming later down the road. Now, if we rewrite this, this is 2 over 1 minus 9 over x squared. And it's easy to see now that if x goes to infinity, certainly 9 over infinity squared is going to 0. Or if x went to negative infinity, 9 over negative infinity squared is going to be 0. So what does that leave me with? That leaves me with 2 over 1. My answer is 2. So now think about this, right? This is what I mean. When you see infinity over infinity, it's not like 7 over 7, which always equals 1. We don't know what we're comparing. All we're saying is it's a big number over a big number. And in fact, in this case, it came out to be 2, right? What that must mean is this infinity is twice the size of this one. This is, right? That's what it's basically saying. So we have a horizontal asymptote of y equals 2. Let's put all this information now on our graph. We know we have vertical asymptotes at x equals -3, +3. We have a horizontal asymptote of y equals 2. And we have an x-intercept of 0. That's all we know, except we do know it's a bouncing intercept, don't we? So we could always pick some more points if we're unsure to see what's happening. And there's always going to be stuff to the right of this asymptote, in between. There's going to be a graph, and there's going to be something to the left. So let's say we start over here. Now you can always pick a number bigger than 3, but I can already tell you what the graph is going to look like. Think about your options. We know that if there's a vertical asymptote, your graph has to approach it either like this or like this, right? It has to approach infinity or negative infinity. And it also has to approach 2. So it has to be approaching from above or below. If it was this, if the graph had to go from here to here, do you see that there would be another x-intercept? It would have to cross the x-axis. But we know that there was only one x-intercept, which was 0. So it can't be the bottom. It has to be this. Now, again, you could confirm that. If I plug in 4, for example, if I do f of 4, remember my function here, I'll write it back up here, is 2x squared over x squared minus 9. That's going to be 16 times 2 is 32 over, this is 32 sevenths. So it's something positive. Remember that we designated this as an opposite vertical asymptote. So if we feel confident that it looks, the graph is going up on this side, then it has to be going down on the other side, right? It must be coming down here. And we know this was a bouncing intercept. So we know it's going to bounce off and come down. Now, we also remember that we decided this was an even graph. So the one thing we could do is just match, if this is the right half, the left half, it has to look just like this reflected over the y-axis. But you can still just, if you didn't even notice that, we know this has to bounce. And if it bounces, it's going to be headed back down this way. And for the same reason over here, I know that on this side of the asymptote, which is also an opposite, the graph has to be coming up, right? If it goes down on this side, it has to be going up. And then it would make sense it has to approach my horizontal asymptote as x goes to negative infinity. Notice it has that even symmetry, right? So it did look like what we expected it to look like. All right, let's do one more on this video. And I'm going to make some more videos where we're going to practice graphing. You need to see a lot of these to get really good at it. Let's do one more here. I don't expect this to be odd or even because I've got an x and some kind of, I can see if I FOIL that out, I'm going to have an x squared and then an x. So it's probably not odd or even. So let's go straight to my x-intercepts. If I set this equal to 0, fraction's only 0 if the top is 0. So it's just x equals 0 and it's x to the first. That's an odd power. So I know this is a through intercept. It's also the origin. So I know my y-intercept is going to be 0 as well. So let's talk about our vertical asymptote. F of x is undefined when x plus 3 squared equals 0, which gives me -3. But this time, this -3 came from something from an even power. And that's what we are predicting then. Our vertical asymptote is going to do the same thing on either side of the vertical asymptote. It's going to behave the same way. It's going in the same direction. And then for our horizontal asymptote, well, if I imagine x getting really big, that's infinity. Infinity plus 3, if I square that, that's also infinity. But what hopefully you learned from the last problem is when you get infinity over infinity, it's anybody's guess, right? We don't know what's going to happen unless we do some work on this and investigate it a little bit more. What I'm going to do, I'm going to do some dividing, but what I want to do first is FOIL out the bottom. You should be able to do that. X squared plus 6x plus 9. And my rule from the previous page, right, we're going to divide each term by the biggest power of x in the denominator, which is x squared. So we'll divide this by x squared, x squared, x squared, x squared. Let's see what we're looking at. X over x squared is 1 over x. This is 1 plus 6 over x plus 9 over x squared. If x becomes really big, both positive or negative, 1 over a really big positive or negative is going to 0. This is going to 0. 9 over something infinity squared is going to also go to 0. So what does that leave me with? On top, I have 0, but on the bottom, I have 1, and 0 over 1 is 0. So my horizontal asymptote is y equals 0. So yeah, this time, think about this. Infinity over infinity was the original form of our limit. It actually equals 0. Or we should say it's approaching 0, right? Let's draw our graph. So we have horizontal asymptote of 0. So that's the x-axis, so we'll dash that. Vertical asymptote of x equals -3. And we have an x-intercept of 0, and it's going through. So it's either like this or it's like this, right? So here I really have I need more information. I can't tell you what it's going to do just with that information. So maybe what we want to do is let's find out, we want to see if it's going, as it gets close to this asymptote, whether it's going to infinity or negative infinity. So maybe we plug in something between 0 and -3, like f of, let's try -1. My function was x over x plus 3 squared. So it'd be -1 over -1 plus 3 squared. That's -1 over 2 squared. It's -1/4. So when x is -1, we're down here, -1, -1/4. So that kind of indicates that our graph is negative. It's going to just keep going down like this, huh? Now, because this was a same vertical asymptote, that means the other side of the graph is going down to negative infinity as well, which means we probably, all indications are, would just approach 0 in this direction. But here's something that may be surprising to you. Remember that we found out this x-intercept was going to go through the x-axis because it came from an odd power. So what has to happen is this graph is going to go through here. Now, it does have to approach my horizontal asymptote of 0. So at some point, it has to come back down and start to approach 0 like this. Now, why might that trouble you? This is saying then my graph looks like it's crossing my horizontal asymptote. And there's a lot of people who, when they see that, kind of freak out, like something must be wrong. What I want to tell you is it's okay for your function to cross your horizontal asymptote. And why is that? Remember, the only reason we put a horizontal asymptote of 0 was we were just trying to say that the function gets to close to 0 when x goes towards infinity, which is over here, it's getting close to 0. And over here, towards negative infinity, it's getting close to 0. This doesn't say anything about what happens, when you're not at infinity, which means it's okay for the graph to be equal to 0 because you're not anywhere near infinity. Okay, if your graph has to cross the horizontal asymptote, it's okay. It's okay. If it needs to cross to do what you think it should be doing, it's okay. Now, it can never cross a vertical asymptote because it's always undefined here, right? So there's no way it could ever pass right through that vertical asymptote, but it's okay to cross a horizontal asymptote. If you're working on these, what I would suggest is try sketching them with the strategies we've done now. You could check yourself, obviously, using Desmos or some other graphing calculator tool, and just see that you're doing it right. The goal is, however, to be able to do this by hand without relying on a calculator. So, just make sure you're seeing all the steps and how they all fit in together. And again, I will make at least another video on graphing more of these rational functions so that we can see more examples.